Okay, so we're going to talk a little bit about topic 2.2. It's a separate homework. Here 2.1 is its own homework and 2.2 is its own homework. So I don't know if we'll get through all this today, but we'll try to get through at least some of it because we still have like 20 minutes. So we're talking about introduction to functions. So just like with graphing lines, when you plug a value in for x, when you were using that t-chart, you got something specific out of it for y, and that's actually called a function. Sometimes, do you remember that those equations might have had like an f of x in front of it when you were graphing? So like, I'm going to just add for extra information. We might have said f of x equals 2x plus 1. All that means is the function of x, when I plug x into this, what do I get it? But we're used to just saying, when you see the function of x, we're going to call that y. Because it just makes more sense to us to not have f of x beside it. And so with these functions, that's really all we're doing is, like if it says let f of x equals x squared minus 1 and evaluate, and it's going to tell you what you're plugging in for the x value. Sometimes it's just a number. Sometimes it might be an expression. So let's go look at these 5 examples. So this one is just saying f of negative 5. Okay, so that means all you're doing is in that function they gave you. I'll rewrite it probably for each one so that you can see it. All you're doing is plugging that in for x. Okay, so if I said the f of negative 5, we're saying negative 5 squared minus 1. So really you're not doing anything on the left. That's just function notation. It's just a fancy way to show what we're doing on the right. So what's negative 5 times negative 5? 25. And what's 25 minus 1? 24, right? Okay, well again, if we have the function of x equals x squared minus 1. That's what we're working with, that same function. If I'm saying let's plug 3b in for x, that's what's going right there. So let's say we have 3b, and that's in a parentheses squared minus 1. So we need to simplify this. We can take 3b times 3b, right? Do you guys remember? It's like saying 3b times 3b is 9b squared. Are those like terms? 9b squared minus 1? We're done, because they're not like terms. We're going to say that's our answer. So sometimes in this assignment, your answer is going to be an expression. We're not going to know what it is. Okay, this time it's kind of like we're saying we're taking 3 times whatever the expression becomes when you plug b in for x. Okay, so again, remember the function. I keep writing it because it just helps with the visual. We're plugging this in for x. And then it's kind of like in the end you would multiply that times 3. That's really all that's meaning, that extra 3. So underneath here, let's write 3 times. And then what are we plugging in for x? Just a b. Since it's not a 3b, I didn't put it in a parentheses because I know by saying b squared, isn't it just b squared? Easier way, we can just kind of skip that step. Now we would want to distribute 3 times that and 3 times that. So we have 3b squared minus 3 times negative 1 is 3. So again, this might be a little, if that's confusing, just mark through that so that you can see what was happening. The function of x is just kind of there. We're really focusing on that x squared minus 1, plugging it in. Okay, this time x is an expression a plus 3. So again, if we have our function of x above is equal to x squared minus 1, we are taking this and plugging that in for x and then squaring that parentheses. So we're saying a plus 3 squared minus 1. Do you guys remember FOIL? We have to write this out twice. A plus 3 times a plus 3 minus 1, and we have to expand that. We have to FOIL it. So a times a is a squared. A times 3 is a positive 3a. Do you remember that? First times first, outer. And then your inner, 3 times 3a is a positive 3a, and 3 times 3 is 9. And then I'll go ahead and bring down minus 1. So you have like terms here that can combine, and like terms on the end that can combine. So you would answer this one, a squared plus 6a, 9 minus 1 is 8. So the last example on this page, it's like you're doing two separate things. Again, remembering that function they gave us was the function of x equaled x squared minus 1. So we're doing it twice, and then we're going to have to add them together because you have a plus sign between the two with those little f's in front. Functions. So function of the x, basically you're like replacing it with an a once, and then we're going to say plus when the x is a 3. So the way that would look is, remember you're still just plugging it in for x, is this first one right here would look like a squared minus 1. And I'll do the other one like in a different color. And then we would say plus, and this time I'm replacing my x with a 3, so 3 squared minus 1. So I can't really simplify that, but I can kind of remove the parentheses, can't I? There's nothing really happening, but I can come over here and simplify. What's 3 squared? 9. So let's just say 9 and bring down minus 1. Then we could just do it all at once, all that combining like terms in the end. Remember when you're adding polynomials together, it's like you're shedding the parentheses and combining any like terms that you might have between the two. There's not any like terms between your a squareds, but then we have negative 1, 9 is 8, minus 1 is a 7, so plus 7. So whatever's in that parentheses is all you're going to be changing inside like the function they give you. And I kept rewriting it just because, especially when we're doing all of these, so that you could be zoomed in, you know, you're using this on all of them. All of these are the same thing, and you're just replacing x for whatever they tell you to do. The only thing that's a little weird was maybe the c. If you have a 3 in front of that function of when x is b, you would multiply it in the end times 3. But we're all using that same x squared minus 1. When you do your WebAssign homework, it's going to be similar. You're going to have like one function, and then it's going to tell you like an A through E or something, where you have to do the same function but with different stuff, plugging it in for your x. Let's turn the page, and we'll talk about domain. So this is why interval notation was important to learn. Because when we find the domain of something, we want to express it in interval notation. So the domain, basically it's almost like thinking about what x can be or maybe what x cannot be, you know, like a restriction. If you think about this function right here, we can never have 0 in the denominator, right? So you might think, what can x not be? So if we just set the denominator equal to 0, then we're going to find the value of x that x couldn't be, so we can find what x could be. So if you just pull that down, you're only working with the denominator when it's a fraction like that, and we're just thinking what would make the denominator 0. And if you add 2 to both sides, you'll find that when x is 2, that's going to 0 out that denominator, right? So we want to say x cannot be, so I'm going to put a red line through there, x cannot be 2. But x could be any number other than 2, correct? Right? So let's look and see what that would look like on a number line. So if I just had 2 here, so we can't include 2. So are we using soft or hard brackets? Soft. We can't include it. So we have what we would have is, in one way, we would have a soft bracket pointing to the right to positive infinity. And in another, we're pointing to the left and going to negative infinity. And so a fancy way to say that, this would be like a union. Even though you don't see a gap, the 2 itself is your union. The number 2 is the union. So the way you would write this is, remember, you can never ever attain infinities. So there's always soft brackets here. So you have a soft bracket, negative infinity, comma 2, with a soft bracket by 2. And then you have U for union. And then a soft bracket going the other way because we're starting here going to infinity. So 2, comma, positive infinity, soft bracket. And it's going to ask you to answer that in interval notation. It doesn't ask you to do set builder notation, but that would just be like you're working with it here. If you had set builder, to kind of remind you what it means, your domain would be x such that, kind of gives a restriction, x does not equal 2 is what that would look like. The values of x such that x does not equal 2. Could be any of those values. If it's a radical, what do you think it couldn't be in terms of a radical?
Negative number.
A negative number, because we can't have imaginary numbers. Can you graph something that's fake? No. Imaginary, not real. We can't graph that. So we would not want like a negative number. That's what we don't want, right? And here we just don't want 0 in the denominator, whatever this is. Okay, just quick reminders of notes what that means, why we do what we do with each type. So you're going to take the expression underneath, and we would need x minus 4 would need to be greater than or equal to 0. So what that means is, if you isolate that, you're adding 4 to both sides. So x is greater than or equal to 4. So think about that. If you were to plug any number that is 4 or greater than, you would get a positive number under there, right? If you plugged in any number lower, that'd be like saying 3, because 3 is smaller. 3 minus 4 would make that a negative number. So there is a restriction, and it's just stating any number greater than 4 could be a solution. So what that means on the number line, working with those hard brackets this time, because you have an or equal to, right? I don't know why I put negative 4, but 4. So we're using a hard bracket, and we're pointing to positive infinity. So as interval notation, this one would look like hard bracket to the left of your 4, comma, positive infinity with a soft bracket. Infinities always have soft brackets. Hopefully this is an extra review for your interval notation that we went over. Do you think there's a restriction in number 3? You could plug in a positive number, a negative number, and you're going to get a number, right? There's like nothing that's going to make a denominator 0. There's nothing, any of that. It's not going to make it imaginary. We can graph negative numbers. We can't graph imaginary numbers, right? So this one, if you have just an expression that's not a fraction, not a radical, you're going to say that the answer could be all real numbers. Meaning, not any negatives. And the way you would indicate that in interval notation would just be like saying negative infinity to infinity. So for our brains, we're going to stop there today.